abandoned mine shaft. The movement provides clues to strains and stresses deep in some places on Earth, the stress on the crust becomes so great and sets off earthquakes and volcanic eruptions. The terrifying forces inside the Earth were long believed to be of supernatural origin. Some 2,000 years ago, when an earthquake and the eruption of Vesuvius destroyed the city of Pompeii, Roman citizens thought that the gods were angry.
In the 2nd century, a Chinese scholar invented the first known instrument to detect earthquakes. It consisted of 8 dragons on a bronze vessel, each of them holding a metal ball in its open mouth. Around them sat 8 toads. Inside the vessel, an inverted pendulum was balanced on a point. When an earthquake occurred, the device gave a general idea of its direction.
In the 17th century, the Italian Francisco Trevini devised a more accurate instrument. He suspended an iron weight from a wooden frame that was anchored to the ground. Whenever the earth shook, the frame moved with it. But the pendulum was kept almost motionless by inertia and traced a line in the sand beneath it. Trevini assumed correctly that an earthquake generates waves that travel through the earth somewhat as waves travel through water. Modern seismology, the scientific study of earthquakes, has added greatly to Trevini's limited knowledge.
When an earthquake occurs deep underground, 2 kinds of waves with different velocities are set in motion. The faster is called the P wave, and the slower the S wave. The P wave moves through the earth much as the coils move in this spring. But the S wave travels with an altogether different motion. When a quake occurs at a shallow depth, still other waves are generated, which travel along the surface of the Earth. Near their source, surface waves are often destructive. But even after they have lost the power to destroy, they, like all earthquake waves, can be detected seismographs.
Far more sensitive than Trevini's simple device, it still makes use of the pendulum principle. When the earth trembles, the pendulum drives a recording pen to trace the seismic waves. Modern seismographs are so sensitive that they can detect even surface disturbances. The pounding of the sea generates signals called microseisms that travel through the earth and can be recorded at nearby observatories. Microseisms can also be caused by hurricanes and other large storms. While seismographs can actually be used to track hurricanes, their primary function is to record the waves generated by earthquakes. The analysis of these seismic recordings, or seismograms, provides the scientist with his basic knowledge of disturbances underground. Seismologists can identify the various seismic waves and compute the speed at which they travel. With the help of this information, to pinpoint its exact location, at least 3 stations pool their records of the same quake. For each station, a circle is drawn, using as a radius its distance to the disturbance. The earthquake is located at the point where the 3 circles intersect. Every year at observatories all over the world, seismographs record thousands of minor earthquakes and hundreds of major ones. As with many of the geophysical sciences, International cooperation is essential, for only by comparing records of the same disturbance can seismologists arrive at a meaningful picture of events deep inside the Earth. Although we still know very little about the causes of earthquakes, the waves they generate have helped man in his effort to penetrate to the depths of our planet, to explore the structure of the hidden Earth.
About 50 years ago, a Croatian seismologist named Mohorovičić discovered that when an earthquake occurs, certain waves are refracted or bent back to the surface. He reasoned that this was caused by a change in the nature of the rock inside the Earth. When similar findings were reported all over the world, seismologists concluded that the Earth has a crust, a thin outer shell. The lower boundary of this crust is called the Mohorovičić discontinuity, or MOHO, in honor of its discoverer. Some earthquake waves pass through the MOHO and have revealed much about the rock layer beneath the crust, called the mantle. But at a certain distance from the quake, a curious shadow zone was observed in which P waves could not be recorded. Seismologists concluded that deep inside the Earth there is a second change in the nature of the rock, which deflects these waves. Moreover, S waves also produce a shadow zone. Since they cannot travel through liquid, it was assumed that a region of hot molten material exists at the center of the Earth, called the core. Each of the regions, core, mantle, and crust, is known to have several subdivisions.
The surface of the crust is man's natural home. Over millions of years, wind and water, heat and cold have carved out an endless variety of land formations. Wherever rivers have cut deep canyons into the crust, we can glimpse layers of rock just beneath the surface. But to explore and study layers that man cannot see is the work of exploration seismology. Since earthquakes and the waves they generate are beyond man's control, the seismologist uses a series of artificial explosions whose timing and location can be carefully planned. The seismologist prefers to set off his charges in a lake, river, or lagoon. For an explosion underwater generates stronger seismic waves than those in the ground. The size of the charge depends on the depth of the layer to be investigated. Waves generated by explosions are higher in frequency than those of earthquakes and can be detected by special microphones called geophones, which are buried in the ground. Much of the work on seismological expeditions is carried out by students as part of their university training.
Prepare to fire!
Shortly before the blast, a check is made of the electronic equipment that will record the seismic waves. The seismic waves generated by the explosion are picked up by the geophones, amplified, and recorded on photosensitive paper. They provide the scientist with clues to the layering and thickness of the crust. The lines on this seismogram are records from the 36 geophones used in the experiment. The changing pattern of the waves reveals the rock structure of the crust. For example, this intensification of the pattern was caused by a limestone layer. By calculating the rate at which the waves travel, the seismologist can compute the depth of the various layers and determine the structure of the crust. Almost 3/4 of the Earth's crust lies underwater, and to explore it, the seismologist goes to sea. Two ships are used. One carries the hydrophones. The other ship drops the charges. As on land, the seismic waves are bent back by the layers of the crust and recorded. While expeditions on land and on sea have mapped only a small part of the crust in detail, seismologists are beginning to piece together a picture of its general distribution.
Under the oceans, the crust is generally 3 to 5 miles thick. But under the continents, its thickness increases to 15 or 20 miles, and its structure becomes more complex. Where mountain ranges further increase the mass of the continents, the crust is depressed correspondingly into the mantle.
Until recently, the largest unexplored area of the Earth's crust was the continent of Antarctica, concealed under 6 million square miles of ice. To probe its structure, scientists of 12 nations established a network of research stations during the International Geophysical Year. In the Antarctic, explosion seismology had a twofold purpose: to map the topography of the continent under the ice, its mountains and valleys, and to disclose the structure of the crust itself. Scientific work in the polar region is complicated by many factors, for the stations are isolated outposts in a vast expanse of ice. All set.
Seismological expeditions crisscrossed Antarctica and gave man his first glimpse of the continent under the ice. They found that the Andean range of mountains extends all the way from South America into the heart of Antarctica. A second chain of mountains cuts through the continent and separates a region of lowlands from a region of deep valleys and inactive volcanoes. If the ice were ever to melt, the volcanoes would become islands, and the deep central gorge would become part of the Antarctic Ocean.
In many parts of the world, seismology is playing an increasingly important part in industry. In the deserts of Saudi Arabia, a team of petroleum geologists is probing the crust in search of mineral deposits. Using the techniques of explosion seismology, they can locate rock formations under the surface that may indicate the presence of an oil dome. This greatly decreases the margin of error when drilling begins. A new method has been devised to explore layers of the crust without explosions. A mobile laboratory, equipped with special instruments, records seismic waves that are generated when a weight is dropped from the back of a truck. The search for mineral deposits, as well as the general exploration of the Earth's crust, can be carried out with a gravimeter, an instrument which measures gravitational pull. When the scientist notes an increase in the pull of gravity, it indicates either that there is dense rock material in the crust, or that the mantle in the area is closer to the surface. This technique supplements the findings of explosion seismology. Our knowledge of the structure of planet Earth is growing from year to year. We know that it consists of a core, a mantle, and a crust. And we know something about the composition and distribution of the crust. But many fundamental questions remain unanswered. What was the origin of our planet? What forces shaped the Earth? The work of seismologists who are probing the interior of the Earth along with the findings of another science, astronomy, may bring us closer to the answer. Astronomers, looking far out into the universe, have acquired some understanding of the birth and death of stars and galaxies. They have formulated theories about the creation of our own solar system by observing events millions of light years away.
Our solar system may have begun with an enormous cloud of gas. Under the force of gravity, this cloud began to condense. The main focus of attraction was in the middle of the cloud, but because of irregularities, a number of smaller centers appeared. The main nucleus continued to grow, and its temperature rose until it reached several million degrees. It is thought that in this way the sun was born, radiating huge amounts of energy. The smaller masses of matter became the planets, among them the Earth and its sister planet, the Moon. The planets were still surrounded by uncondensed material, but intense radiation from the sun may gradually have blown most of the cloud away, leaving the space around the planets clear and almost empty. Some scientists think that the Earth at this time consisted of a core surrounded by a cooler covering. An alternate theory suggests that the Earth was created cold and that heat was built up gradually by the decay of radioactive minerals.
Whatever their origin, reservoirs of intense heat exist inside the Earth today. Some of this heat escapes in the form of volcanic eruptions. Streams of molten rock, at temperatures of thousands of degrees, pour down the side of the crater. Modern science has dispelled much of the mystery that long shrouded the origin of volcanoes.
Today we believe that a volcano begins with fracturing in the Earth's crust. The fractures relieve the pressure on the hot, compressed rock in the mantle and cause it to become liquid. The liquid rock rises through the cracks and erupts at the surface. When the eruption subsides, layers of lava and volcanic ash solidify on the ground around the fracture. Each eruption deposits new layers of lava and sometimes ash, gradually building up a cone-shaped mountain, the volcano.
In many parts of the world, people live and work in the shadow of volcanoes. For volcanic ash and lava, carrying minerals from great depths, have created some of the most fertile farming regions on Earth.
When a volcano dies and the hot lava recedes, the surrounding Earth cools and cracks. Groundwater seeps through the cracks. When it reaches rocks which are still hot from the lava, the water boils and rises to the surface, most often in the form of geysers.
Man has learned to use the heat buried in the Earth. The volcanic region of California, engineers are building an experimental plant to harness natural steam for industrial purposes. The steam will provide the power for driving electric generators. In Italy, New Zealand, and Iceland, countries where there has been extensive volcanic activity, plants drawing on reservoirs of thermal energy are already in operation.
Scientists have plotted the distribution of volcanic regions on Earth and noted an important fact. The crust of our planet is marked by clearly defined volcanic belts. Moreover, when they plotted the zones of greatest earthquake frequency, seismologists found that the two belts almost coincide. The reasons for this are still unknown, and subject to speculation. Earthquake zones generally occur where the thick crust of a continent merges with the thin crust under the ocean. This is a region of potential weakness. Perhaps the hot mantle exerts pressure on the crust, and when the strain becomes, the crust fractures and an earthquake occurs. If the fracturing reaches all the way from the mantle to the surface, molten rock rises and erupts as a volcano. This is one possible explanation for the relationship between earthquakes and volcanoes.
The crust under the ocean, where earthquakes and volcanoes occur just as they do on land, is of particular interest to the scientist. During expeditions in the Pacific and Atlantic, special thermometers were used by oceanographers to measure the heat flowing out of the crust at the bottom of the sea. Temperature readings in the Atlantic have indicated that heat is more intense along certain rifts or cracks in the ocean floor.
Some scientists believe that these rifts are part of an enormous fracture system, some 40,000 miles long and extending around the entire globe. It has been suggested that the Earth is actually expanding and that the rifts are places where the crust is pulling apart.
Seismologists are continually seeking to probe deeper into planet Earth. An oil rig is being prepared to drill through the thin crust under the ocean. Scientists hope that this will make it possible for them to make deeper and more accurate heat flow measurements, to sample the sediments on the ocean floor, to explore thoroughly the many layers of the crust, and finally, to bring back a piece of the mantle itself so it can be examined for the first time. The space age has opened up new research possibilities for the seismologist. A small quartz seismograph has been designed for the day when scientific instruments can be landed on the moon. Scientists hope that when a seismograph is landed on the moon, it will answer questions that have long puzzled man. What is the nature of the moon's crust? Are its craters of volcanic origin that have a core? Since the moon was presumably created at the same time and of the same materials as the Earth, the answers to these questions may give man new information about the origin and structure of his own planet. But to fill in the main gaps in his knowledge, the seismologist must continue to look to the interior of the Earth, his principal laboratory. Seeking new information and insights, man must intensify his of earthquake waves. He must observe the surface effects of forces that originate deep underground and increase his understanding of their basic causes. He must perfect his current techniques for probing far below the surface. And he must continue to experiment with new techniques. For only by advancing along a broad front can man hope to solve the many mysteries of the hidden Earth.